The world is witnessing weather at its most ferocious. From continent to continent, nature's fury seems to be growing stronger. We see towering flames devouring forests in minutes. We see ocean waves swallowing coastal homes during powerful hurricanes. Rivers are overflowing their banks, turning streets into raging torrents. At the same time, other parts of the world are cracking under intense heat and prolonged drought. These are not just isolated incidents anymore. They are becoming the new, unsettling norm. Each event leaves behind a trail of devastation, impacting lives and reshaping landscapes. We are only beginning to comprehend those changes. The sheer scale and frequency of these events demand our full attention. We are all connected to this story. No corner of the globe is entirely safe from the reach of extreme weather. The images on our screens are more than just news reports. They are urgent warnings. A wildfire on one side of the world can fill the skies with smoke thousands of miles away. A hurricane in the tropics can disrupt global supply chains, affecting economies everywhere. These events raise simple but profound questions that deserve clear answers. What is happening to our planet's climate? Why are storms, floods, and fires becoming so much more intense and destructive? It has become impossible to ignore the signs. Understanding these phenomena is no longer just a task for scientists. It is a necessity for everyone. The safety of our communities depends on it. The future of our infrastructure relies on it. Our ability to grow food and access clean water is tied to it. When a superstorm approaches, knowing its path can mean the difference between life and death. When a heat wave descends, understanding its dangers can protect the most vulnerable among us. This is why the topic matters now more than ever. We are moving from a state of shock to a quest for science-based knowledge. These extreme events are not random acts of chaos. They are the results of complex, interconnected systems governing our planet's atmosphere and oceans. The energy that fuels a hurricane is rooted in the same principles that create a gentle sea breeze. The conditions that lead to a devastating drought are linked to the global water cycle that brings us life-giving rain. To make sense of the chaos, we must first understand the order. This documentary promises to provide clear, calm explanations for these powerful forces. We will peel back the layers of complexity and reveal the science in a way that everyone can grasp. This 20-minute deep dive is structured to guide you from confusion to clarity. We will embark on a journey through the science of our planet's weather engine. Our exploration will be broken down into 4 distinct parts, each building upon the last. First, we will start with the fundamentals. We will explore how weather actually works, looking at the basic forces like atmospheric pressure, ocean currents, that set the stage for everything that happens in our skies. We will demystify the processes that turn simple clouds into massive, continent-spanning storm systems, providing a solid foundation for all that follows. Next, we will confront the giants of extreme weather head-on. We will take a closer look at the major events that capture headlines around the world. We will dissect the anatomy of hurricanes, from their swirling eyes to their destructive storm surges. We will investigate the silent threat of heat waves, the sudden danger of flash floods, and the terrifying speed of wildfires. By examining these events up close, we can better appreciate their power and the specific conditions that allow them to form and intensify. This section will connect the basic principles of weather to their most powerful and dangerous expressions. After exploring what these events are, we will turn our attention to why they are changing. The third part of our journey examines the human connection. We will investigate how our actions, from greenhouse gas emissions to the expansion of our cities, are amplifying weather-related risks. It is crucial to understand how a warmer climate provides extra fuel for storms, and how urban landscapes can worsen the impacts of heat and rain. We will also look at who is most at risk and why some communities are more vulnerable than others when disaster strikes. Finally, we will look toward the future, focusing on prediction and preparedness. Knowledge is our most powerful tool for building resilience. In our last section, we will showcase the incredible technology that allows us to forecast extreme weather with growing accuracy, from advanced satellites to sophisticated computer models. We will explore the early warning systems that save countless lives and the practical strategies communities are using to adapt. This journey will bring you close-up human stories and the clear science behind the headlines, preparing you to understand our changing world. All weather on Earth begins with a single, powerful source, the sun. Our star is a giant nuclear furnace, constantly beaming energy across 93 million miles of space. This solar energy is the fundamental driver of our planet's climate system. However, Earth is a sphere, which means the sun's rays do not strike its surface evenly. The equator receives direct, concentrated sunlight. The tropics receive direct, concentrated sunlight. The polar regions receive sunlight at a sharp angle. That spreads the same amount of energy over a much larger area, making it colder. This creates a massive temperature difference between equator and poles. That imbalance of heat sets our atmosphere in motion. Nature constantly tries to find balance. Heat moves from warm equatorial regions toward cold polar regions. This perpetual transfer of energy is the engine that powers all weather. Think of it like a giant planetary heating and cooling system. The atmosphere redistributes heat. The oceans redistribute heat. Without that movement, the tropics would be unbearably hot. The poles would be even colder. Every breeze and every cloud is part of this process. The sun also heats the planet's surface. Different surfaces absorb and release heat at different rates. Dark oceans absorb a lot of solar energy. Dense forests absorb a lot of solar energy. Bright ice sheets reflect much of it back to space. Light-colored deserts reflect much of it back to space. That differential heating creates localized temperature variations. On a sunny day, land heats faster than nearby ocean. The air over land becomes warmer and lighter. The air over cooler water stays denser. That difference starts a small circulation, creating a refreshing sea breeze. These principles apply globally. Uneven heating is the first step in a chain. Temperature, pressure, wind. Pressure differences drive the winds. A gentle wind rustles leaves. Violent gales form hurricanes. All atmospheric movement traces back to the sun's uneven influence. Understanding this energy balance is the first key to how weather works. The uneven heating of the Earth creates zones of high atmospheric pressure, low atmospheric pressure. Warm air is less dense and tends to rise, creating areas of lower pressure. Conversely, cold air is denser and sinks, creating areas of higher pressure. Air flows from high to low pressure. That movement of air is wind. This drives vast rivers of air around the planet. Global wind patterns transport weather systems across continents and oceans. They shape the climate of different regions. If Earth didn't rotate, winds would flow straight from the poles to the equator. But Earth spins on its axis. That spin creates the Coriolis effect. In the northern hemisphere, it deflects air to the right. In the southern hemisphere, it deflects air to the left. That's why hurricanes spin counterclockwise in the north and clockwise in the south. Coriolis breaks the north-south flow into circulating cells, trade winds, jet streams. These wind patterns define boundaries between huge bodies of air. Those are called air masses. When two different air masses meet, they don't mix easily. They form a boundary called a front. A cold front is when dense cold air pushes into warmer air, forcing the warm air to rise rapidly. That often causes thunderstorms and sharp, sudden changes in weather. A warm front is when lighter warm air slides up and over colder air, bringing steadier, more widespread precipitation. Meteorologists constantly track air masses and fronts. They use weather maps with lines and symbols to show highs, lows, and fronts. By tracking movement, forecasters judge whether a region will see clear skies, rain, snow, or severe storms. The daily weather forecast is a report on the movement of these air masses and fronts. The atmosphere is not the only system working to balance the Earth's temperature. The world's oceans play an equally critical role, though often slower. Water has a much higher capacity to store heat than air does. The oceans act as a massive global reservoir of thermal energy, absorbing huge amounts of solar radiation in the tropics. This stored heat is then transported around the planet by a network of powerful ocean currents. This system of circulation is often called the global ocean conveyor belt, a slow but immensely powerful force that shapes climates worldwide. This conveyor belt is driven by differences in water temperature and salinity, salt content. Warm surface currents, like the famous Gulf Stream in the Atlantic, flow from the equator toward the poles. As this water travels north, it releases heat into the atmosphere, which warms the surrounding air. This is why Western Europe has a much milder climate than similar latitudes, like parts of Canada. The warm, salty water eventually reaches the North Atlantic, where it cools, becomes denser, and sinks deep into the ocean. This sinking water then begins a slow journey back toward the equator in the deep ocean. The process is a continuous loop. The deep, cold water eventually works its way through the world's oceans, slowly warming and rising back to the surface, primarily in the Pacific, and primarily in the Indian. Once at the surface, it is heated again by the tropical sun, and the cycle repeats. This entire journey can take hundreds of years to complete, or even thousands of years. While slow, this circulation is vital for regulating the global climate. By moving vast quantities of heat from the equator to the poles, the ocean conveyor belt prevents the tropics from overheating and keeps higher latitudes from plunging into a deep freeze. Any disruption to this delicate system can have significant consequences for global weather patterns. For instance, scientists are closely monitoring the potential impact of melting ice from Greenland. The influx of large amounts of fresh, cold water into the North Atlantic could dilute the salty surface water, making it less dense and potentially slowing or altering the sinking process that drives the conveyor belt. Changes in these crucial ocean currents can lead to dramatic shifts in temperature and precipitation patterns across the globe, illustrating the deep connection between the ocean and the atmosphere. The movement of heat is just one part of the weather story. The other crucial ingredient is water. The water cycle, also known as the hydrologic cycle, describes the continuous movement of water on the surface, above the surface, below the surface of the Earth. It is a closed system. The total amount of water on our planet remains relatively constant over time. This cycle begins with evaporation. The sun's energy heats the surface of oceans, lakes, and rivers, turning liquid water into a gas called water vapor. This invisible vapor rises into the atmosphere, carrying with it a tremendous amount of energy. As the moist air rises, it begins to cool. This cooling causes the water vapor to undergo condensation, changing back into tiny liquid water droplets or ice crystals. These droplets are so small and light that they can remain suspended in the air, clustering together to form the clouds we see. For precipitation to occur, these tiny droplets must grow much larger. They do this by colliding and merging with other droplets. When they become heavy enough to overcome the upward air currents that are holding them aloft, they fall back to Earth as rain, snow, sleet, or hail. This process of condensation and cloud formation releases the energy that was originally stored in the water vapor during evaporation. This released energy, known as latent heat, is a powerful fuel source for storms. It warms the surrounding air, causing it to rise even faster, which in turn draws in more moist air from below. This creates a self-sustaining cycle that can cause a small, puffy cumulus cloud to grow into a towering cumulonimbus, or thunderstorm cloud, in a matter of hours. This release of latent heat is the engine that powers everything from afternoon thunderstorms to massive hurricanes. Once precipitation reaches the ground, the water cycle continues. Some of it soaks into the soil, replenishing groundwater. Some of it flows over the surface as runoff, collecting in streams, rivers, and eventually returning to the ocean. The rest evaporates back into the atmosphere, starting the cycle anew. The intensity of this cycle can change. Warmer air can hold more moisture, meaning there is more water vapor available to fuel storms. This can lead to heavier rainfall and more intense flooding, linking the fundamental water cycle directly to the increasing frequency of extreme weather events we are witnessing today. Hurricanes are among the most powerful and destructive storms on Earth. They are also known as typhoons, tropical cyclones, depending on where they form. These massive, rotating storms get their energy from warm ocean waters. For a hurricane to form, sea surface temperatures must be at least 26.5 degrees Celsius, 80 degrees Fahrenheit. The storm begins as a cluster of thunderstorms over the warm tropical ocean. As warm, moist air over the water rises, it creates an area of lower pressure near the surface. This causes more air to rush in, which then warms rises and adds moisture to the growing system, creating a powerful feedback loop. As the storm system strengthens, the Earth's rotation, through the Coriolis effect, sets it spinning. Winds begin to spiral inwards towards the center. When wind speeds reach 74 miles per hour, 119 kilometers per hour, the storm is officially classified as a hurricane. At the center of this swirling vortex is the eye, a deceptively calm and often clear area of low pressure. Surrounding the eye is the eye wall, which is the most dangerous part of the storm. Here, the winds are at their strongest, and the rainfall is at its heaviest. The sheer scale of these storms is immense, often stretching for hundreds of miles across. The destructive power of a hurricane comes from several sources. The intense winds can tear roofs off buildings, uproot trees, and turn loose debris into deadly projectiles. The torrential rainfall can lead to widespread flooding far from the coast. However, the most lethal aspect of a hurricane is often the storm surge. This is a large dome of water, sometimes over 20 feet high, that is pushed ashore by the powerful winds. The storm surge can inundate coastal communities, destroying homes and infrastructure in its path. It is a catastrophic rise in sea level that happens quickly and with immense force. Around the world, different regions face these powerful storms under different names. In the Atlantic, they are hurricanes. In the Northeast Pacific, they are hurricanes. In the Northwest Pacific, they are called typhoons. In the South Pacific, they are known as tropical cyclones. In the Indian Ocean, they are known as tropical cyclones. Regardless of the name, their formation process and devastating impacts are the same. Satellite imagery allows us to track these giants from space, watching them churn across the ocean. These images are vital for forecasting their path and intensity, giving communities precious time to prepare for the inevitable and powerful impact. Section 2. Heat waves, the silent killer. Unlike the violent spectacle of a hurricane, a heat wave is a quiet and, invisible disaster. It is defined as a prolonged period of excessively hot weather, which may be accompanied by high humidity. Heat waves occur when a high-pressure system settles over an area for an extended period, sometimes for days or even weeks. This system acts like a lid on the atmosphere, trapping warm air and preventing it from rising. The sinking air compresses and heats up, while the sun's rays continue to bake the ground. This combination causes temperatures to climb far above normal levels, creating dangerous conditions for people, animals, plants. Heat waves are particularly dangerous in cities due to a phenomenon known as the urban heat island effect. Concrete asphalt, dark rooftops absorb and retain more of the sun's heat than natural landscapes like forest fields. At night, these materials slowly release the stored heat, preventing the city from cooling down effectively. This means that urban residents experience little relief from the oppressive temperatures, even after the sun sets. The lack of green spaces and the waste heat generated by vehicles and air conditioning units further intensify the effect, turning cities into sweltering traps during a heat wave. The health risks associated with extreme heat are severe. When the body cannot cool itself down effectively, it can lead to heat exhaustion and, in worst cases, heat stroke, which can be fatal. The elderly, young children, outdoor workers, individuals with pre-existing health conditions. High humidity makes the situation even more dangerous because it prevents sweat from evaporating. During a severe heat wave, hospitals often see a sharp increase in emergency room visits for heat-related illnesses, putting a major strain on healthcare systems. Heat waves do not just impact human health, they have far-reaching consequences for the environment and the economy. Extreme heat can wither crops, leading to food shortages and financial losses for farmers. It can strain power grids as millions of people turn on their air conditioners at the same time, sometimes leading to blackouts when they are needed most. Water resources also come under pressure as demand for drinking water irrigation increases. As global temperatures continue to rise, scientists warn that heat waves are becoming more frequent, more intense, and longer lasting, making this silent killer an ever-growing threat. Section 3. Floods. Too much water, too fast. Floods are one of the most common and widespread of all weather-related natural disasters. They can occur for many reasons and take several different forms. River floods happen when prolonged rainfall over a large area causes a river to exceed its capacity. The water spills over the banks and inundates the surrounding floodplain. This can be a slow and gradual process. In contrast, flash floods are sudden and extremely dangerous. They're caused by intense, heavy rainfall in a short period. A small creek or a dry urban street can turn into a raging torrent in minutes, leaving little time for people to escape. Another major type of flooding is coastal flooding. It's often linked to storms and rising sea levels. As we saw with hurricanes, storm surge is a primary cause of coastal inundation. Even without a major storm, higher sea levels mean high tides reach further inland. This is called nuisance flooding, or sunny day flooding. It's becoming increasingly common in coastal cities around the world. It disrupts daily life by closing roads, damaging infrastructure, and contaminating freshwater supplies with salt water, even on days with perfectly clear skies. The impact of floods on communities is devastating. Floodwaters can destroy homes. They can destroy businesses and critical infrastructure, roads, bridges, power lines. Floods can contaminate drinking water supplies, leading to the spread of waterborne diseases. The agricultural sector is also hit hard. Floods can wipe out entire crops and saturate farmland, making it unusable for a long time. The process of cleaning up and rebuilding after a major flood is long, difficult, and incredibly expensive. For many families, recovering from the financial and emotional toll of a flood can take years. Emergency responders are on the front lines when floods strike. They conduct daring water rescues. They deliver essential supplies to stranded residents. And they work to manage the flow of water with sandbags and temporary barriers. Footage from flood zones often shows communities coming together, with neighbors helping neighbors to evacuate and clean up. However, the increasing frequency and intensity of heavy rainfall events, a trend linked to a warmer climate, means many regions are facing a future where devastating floods become a more regular occurrence. Testing the limits of our resilience and preparedness. Section 4. Wildfires. A cycle of fire and fuel. Wildfires are a natural part of many ecosystems, but their scale and intensity are growing at an alarming rate in many parts of the world. 3 key ingredients are needed for a wildfire to ignite and spread. Fuel, heat, oxygen. Fuel is any combustible material, dry grass, shrubs, trees. Heat sources can be natural, lightning strike or human-caused, untended campfire, spark from machinery. Once a fire starts, it needs oxygen to burn. Strong winds supply a steady stream of oxygen, fanning flames. Winds push fire rapidly across the landscape. Recent years have seen an increase in megafires, enormous, fast-moving blazes. These fires can burn hundreds of thousands of acres. The conditions are often set by prolonged drought and high temperatures. Drought dries out vegetation, turning forests into tinderboxes. Fires in these conditions can spread exponentially. They can create their own weather system with powerful convective winds, and even form fire tornadoes. These blazes are incredibly difficult and dangerous to control. They can burn for weeks or months, until weather changes, heavy rain, snow finally help extinguish them. The impact extends far beyond burned areas. Smoke can travel for thousands of miles, causing hazardous air quality in cities far from the fire front. That smoke contains fine particulate matter that harms respiratory health. Wildfires destroy homes and force mass evacuations, leaving behind a scarred landscape. After a fire, bare soil is vulnerable to erosion and landslides when heavy rains arrive. Firefighters and emergency crews battle these blazes under extreme conditions. Helicopters drop water. Crews dig fire breaks and work on the ground. Global examples from California, Australia, Siberia, the Mediterranean show this is a worldwide problem. The cycle of drought, heat, and wind is creating a new and dangerous era of fire. Understanding the drivers behind these events is the first step toward learning how to live more safely in a world where fire is an increasingly powerful force of nature. The link between human activity and our planet's climate is now clearer than ever. For over a century, our modern world has been powered by burning fossil fuels: coal, oil, gas. This process releases large amounts of greenhouse gases into the atmosphere, with carbon dioxide being the most significant. These gases act like a blanket, trapping heat that would otherwise escape into space. This is known as the greenhouse effect. While this effect is natural and necessary for life on Earth, our activities have thickened the blanket, causing the planet's average temperature to rise. This global warming is the foundational human connection to the changing weather. One of the most direct consequences of a warmer planet is warmer oceans. The world's oceans have absorbed more than 90% of the extra heat trapped by greenhouse gases. As we saw earlier, warm ocean water is the primary fuel for hurricanes, typhoons, tropical cyclones. With higher sea surface temperatures, there is more energy available to power these storms, allowing them to become more intense. This means stronger winds, heavier rainfall. The basic recipe for these storms hasn't changed, but we are adding more potent ingredients to the mix, supercharging the storms that form over these hotter oceans. A warmer atmosphere can also hold more moisture. For every degree Celsius of warming, the air can hold about 7% more water vapor. This simple fact has profound implications for the water cycle. When a storm system develops, it now has access to a greater supply of moisture. This leads to more intense downpours and increases the risk of severe flooding. We are essentially loading the dice for heavier rainfall events. The entire weather engine is being supercharged by the heat we have added to the system, making its behavior more volatile and extreme. So, the planet is getting, a lot more energetic. Our influence on extreme weather risk goes beyond just changing the atmosphere. How we use land and build our cities also plays a critical role in how vulnerable we are to disasters. The rapid expansion of urban areas has dramatically altered the natural landscape. We have replaced absorbent surfaces like forests, grasslands, wetlands, with non-absorbent concrete asphalt and rooftops. When heavy rain falls on a city, the water has nowhere to go. Instead of soaking into the ground, it rushes over these hard surfaces, overwhelming storm drains, quickly leading to dangerous flash floods. Our settlement patterns put more people directly in harm's way. Development in high-risk areas is increasing worldwide. We build homes in scenic, fire-prone wildlands, the wildland-urban interface. That raises the risk of homes being destroyed by wildfires and makes firefighting more complex and dangerous. The consequences are painfully clear when disaster strikes. A flood minor in a natural landscape becomes a major catastrophe in a paved-over city. When an extreme weather event strikes, it does not affect everyone equally. Social and economic factors play a huge role in determining who is most vulnerable and who is able to recover. Poverty is one of the biggest multipliers of disaster risk. Lower-income communities often live in areas that are more exposed to hazards. Wealthier individuals and communities have the financial means to prepare for a disaster. For those living in poverty, a single disaster can be a devastating blow from which it is impossible to recover. We see this pattern repeat itself in disasters all over the world. Hurricane Katrina in New Orleans, floods in Pakistan. It is the most vulnerable who suffer the most. A truly resilient society is one that protects all its members, ensuring that everyone has the ability to withstand the storm and recover from its aftermath. In the face of more extreme weather, our ability to predict what is coming has become more critical than ever. Fortunately, the science of weather forecasting has made incredible leaps forward. Our first line of defense is a network of sophisticated satellites orbiting high above the Earth. These eyes in the sky constantly monitor the planet's atmosphere and oceans. They provide a continuous stream of data, allowing meteorologists to see storms as they form, track their movements in real time, measure cloud temperature, measure sea surface height. Back on the ground, a vast array of tools provides a more detailed picture. Weather radar is one of the most important. It works by sending out beams of microwave energy that bounce off precipitation, like rain, snow, or hail. By analyzing the returning signals, forecasters can determine the location, intensity, and movement of a storm with remarkable precision. This is how they can warn you about a severe thunderstorm or a possible tornado heading for your specific area. Weather balloons, released twice a day from locations around the world, carry instruments high into the atmosphere to measure temperature, humidity, and wind speed, providing a vital snapshot of conditions aloft. All of this data, from satellites, radar balloons, and ground stations, is fed into some of the most powerful supercomputers on the planet. These computers run complex programs known as numerical weather prediction models. These models use the laws of physics and fluid dynamics to simulate how the atmosphere will behave over the next few hours, days, and even weeks. Forecasters don't rely on just one model. They use ensembles, which means running many different models or the same model with slightly different starting conditions. This helps them gauge the range of possible outcomes and express the level of certainty in their forecast. The result of this immense technological effort is the daily weather forecast we often take for granted. But it is so much more than that. It is a powerful system for seeing into the near future. The accuracy of a 5-day forecast today is as good as a 1-day forecast was just a few decades ago. This progress is a testament to the dedication of scientists and the power of technology. It provides us with the advanced knowledge we need to prepare for extreme weather, turning potentially catastrophic surprises into manageable and predictable events. This ability to see what's coming is the first and most important step in saving lives. Having a good forecast is only half the battle. That information must be communicated effectively to the public for it to be useful. This is the job of early warning systems. These systems are designed to deliver clear, timely, and actionable alerts to people who may be in harm's way. The goal is to give everyone as much time as possible to take protective action, evacuating from a coastline, seeking shelter from a tornado, or finding a cool place during a heat wave. The language used in these warnings is carefully crafted to be simple and direct. Forecasters avoid technical jargon and focus on what people need to know: what the hazard is, where it will happen, when it will happen, and what actions they should take to stay safe. Around the world, investments in early warning systems have proven to be incredibly effective at saving lives. In countries like Bangladesh, which is highly vulnerable to cyclones, improved forecasting and robust warning systems have dramatically reduced the death toll from major storms. Knowing a storm is coming is one thing. Being able to withstand it is another. As extreme weather becomes more common, we must adapt how we build our cities and manage landscapes. Focus: strengthening building codes, new homes in hurricane zones, reinforced roofs, impact-resistant windows, elevated foundations above flood levels. Rethink our relationship with water. A better strategy: green infrastructure. Parks that double as temporary flood basins. Permeable pavements that let water soak in. Green roofs that absorb rain. For heat and drought, focus on cooling and conserving water. Plant trees to create shaded public spaces. On farms, switch to drought-resistant crops. In fire-prone areas, clear, flammable vegetation to create defensible space. This is a shift in thinking. Instead of fighting nature, learn to work with it. Prepare for the world we will live in, not the one we used to know. Prediction and preparedness are ultimately about empowering people. There are simple but effective steps every family can take to be ready. One of the most important is to have a plan. Assemble an emergency kit. Staying informed is crucial. Ultimately, preparedness is a mindset. It's not about fear, but living with awareness. The hope for a safer future lies in our collective ability to use knowledge wisely and build resilience together. We have journeyed through the powerful forces that shape our weather, from the sun's gentle heat to the fury of a hurricane. We have seen how these natural processes, which have governed our planet for millennia, are now being altered by human activity. The science is clear. A warmer world is a world with more energy, and that energy is fueling more extreme weather events. The storms are becoming stronger, the heat waves more intense, the rainfall heavier. This is the new reality we face. Ignoring this reality is no longer an option, as the consequences are felt in every corner of the globe, affecting lives, affecting economies, affecting ecosystems. The shock of seeing weather at its most destructive can be overwhelming. However, as we have explored, shock can give way to science. Understanding the fundamental principles of our climate system is the first step toward empowerment. When we understand why the oceans are warming and how that heat fuels a hurricane, we can better appreciate the urgency of the forecasts. When we grasp the connection between a warmer atmosphere and heavier rainfall, the need for better flood defenses becomes undeniable and concrete. This documentary has aimed to provide that clarity. We started with the basics of how weather works, the engine of atmospheric pressure, ocean currents. We then confronted the major extreme events directly, dissecting hurricanes, heat waves, floods, wildfires to understand their anatomy and impact. We examined the human connection, linking our actions to the increased frequency and intensity of these disasters. Finally, we looked at the incredible tools of prediction and the practical strategies of preparedness that offer us a path forward. Grasping the science behind extreme weather is not just an academic exercise, it is a critical tool for survival. It is a critical tool for progress. The power of knowledge is the foundation upon which we can build a more secure and resilient future for generations to come, even in the face of an uncertain climate. The path forward is not easy, but it is clear. Building a resilient future means accepting that change is already here. Resilience is not about preventing every disaster from happening. It is about ensuring that when disasters do strike, we have the strength to endure them and the ability to recover quickly. Hope is found in the firefighter creating a fire break to save a home, the engineer designing a flood-proof building, and the city planner planting a new park where a paved lot once stood. This work is happening now, all around us, and it is a testament to our resolve. As the planet's climate shifts, understanding the forces behind extreme weather matters more than ever. Subscribe to Kendu Global Files for more 20-minute documentaries that help make sense of our changing world.